All right, in this video, let's look at a common application of orbital energy. And we're going to look at some escape velocity problems. So this is a classic scenario where we have the Earth, and on the surface of the Earth, we have a rocket. And the rocket is set to blast off from the Earth. And when it blasts off at some initial velocity, we want to figure out how fast must it be traveling so that it breaks free of Earth's gravitational pull. So meaning like at what speed can I launch it off the face of the Earth so that it will always move away from the Earth and never actually fall back down due to Earth's gravitational pull inward. And because Earth's gravitational pull varies as you get farther and farther away, this is possible to model. So what's going to happen? So as the distance goes to infinity, so r being the distance from the center of the Earth, so we have the radius of the Earth to the surface, so it starts at a position r, and then it's going to go some future value, re plus how high it goes above the Earth. As r goes to infinity, so as we go infinitely away from the surface of the Earth, we know that gravitational potential at that point is zero, because for problems on the order of large distances, we're going to set our zero potential to be at infinity. But what else is going to happen is that rocket will be slowing down the whole time, but never completely stopping. So the other limiting factor is that the kinetic energy of the rocket will also equal zero as we go to a radius of infinity. So at infinity, at that reference point, the kinetic and gravitational potential of the energy will be zero. So what we need to do then is use the surface of the Earth. So we'll call this position 0, and we'll call infinity position 1. So conservation of energy tells us that if the rocket leaves the surface of the Earth with a certain kinetic and gravitational potential energy, by the time it gets to infinity, energy will have been conserved. So E initial has to equal E final, total mechanical energy. Well, we know that this is just the K initial plus the UG initial, and this will be the K at position 1 plus the UG at position 1. Well, what do we know? Position 1 is infinity. So at position 1, the kinetic energy and the potential energy both go to 0. All right, well, what about the initial energies? Well, the initial kinetic energy will be based on 1/2 mv initial squared, and then minus the initial gravitational potential, which will be gm of the rocket, so let's call that mr, mass of the Earth, over, and since I'm beginning at a position r relative to the center of the Earth, this is my initial radius relative to my gravitational potential energy. So here we have an equation with kinetic plus potential equal to 0, which will be at infinity. And we can solve this now for the initial velocity. So 1/2 mv naught squared is equal to g mass of the rocket, mass of the Earth, over radius of the Earth. Now, this mass, 1/2 mv squared, is the kinetic energy of the rocket, so this is also the mass of the rocket. So we see it's independent of that. Multiply by 2, and then divide or square root both sides. So I will get that the escape velocity is equal to the square root of g times the mass of the Earth over the radius of the Earth times 2. So how fast must that be? Well, from the surface of the Earth, I must launch my rocket at 11,200 meters per second, so that that rocket will forever move away from the Earth, but never get pulled back in by Earth's gravity. All right, I want you to pause the video now and then try to solve number 4, the escape velocity for the Mars rover, given the mass of Mars and the radius of Mars. See if you can solve it, and then I'll set this one up and show it to you in a second. Okay, so same concept here. Surface of Mars, rover gets launched. What's its escape velocity? So we know that delta E will be 0. So meaning the total mechanical energy it has when launching will be equal to total mechanical energy at any other given position. We also know that as r goes to infinity, UG will be 0 and K will be 0. So we set up our escape velocity relationship. K initial plus UG initial is equal to 0. 1/2 m V initial squared minus gm times the mass of Mars now over the radius of Mars. Right, that's what really changes. So the mass of the rover itself cancels, and we get the escape velocity will be, now I'm skipping a few steps, but you can see them up here, square root of g mass of Mars over the radius of Earth times 2. And for Mars, given its mass and its radius, we get the escape velocity for the rover would be 5,030 meters per second. Okay, and that is a common application of conservation of energy and using gravitational potential on a scale with which it varies according to the radius. And yeah, that's something that you might see on an AP exam, or especially on a test that you might take in this class.